So hello all, I am Shubhajit, one of the PMRF TAs for this course, and welcome to week 4. Okay, so every week we solve some problems from the previous year assignments, and I hope you all attended Harish's TA session where he was covering problems 1 to 8, and I am covering the rest of the problems from the previous year assignments. Okay. So let's start. Okay. So let us read the first question. It says, or it is asking to find the number of silo 3 subgroups of S4. Okay. So what are the total number of silo 3 subgroups that S4 has? Right. So let's try to see. So first of all, you are aware of the cardinality of S4, right? S4 is a group with precisely 24 elements, which is 2 cube times 3, right? So S4 has cardinality 24, which is precisely 2 cube times 3, right? So you are asked to find the number of silo 3 subgroups of S4, right? So what it means is, so any silo 3 subgroup therefore of S4 will have order 3, right? So we need to find out the number of silo 3 subgroups. So we know that by Silo's third theorem, the number of silo 3 subgroups is 1 plus 3k, and this number divides the cardinality of S4, right? So we know this. So k is some positive integer, k is some non-negative integer. Right? So which implies that 1 plus 3k divides 24, and since 1 plus 3k is relatively prime to 3, we know that 1 plus 3k divides 8, right? So what are the possibilities? Let's try to understand. So either k is 0, which implies that the number of silo 3 subgroups is 1 or 4, right? So for k equal to 0 we get 1, and for k equal to 1 we get 4. So the number of silo 3 subgroups is either 1 or 4. These are the only two possibilities now. Now let me ask you this question. So is can this number be 1? So can the number of silo 3 subgroups be 1? I am audible, right? So there is only one here, Manas. So am I audible, and is my screen visible? Can you confirm? Maybe in the chat. Okay. So let me ask you this question. So we have arrived at this particular computation that the number of silo 3 subgroups is 1 or 4 so far. The number of silo 3 subgroups of S4 is either 1 or 4. So my question is, can it be 1? Can the number of silo 3 subgroups of S4 be 1? So just keep in mind that S4 is the group of permutations of 4 letters, right? That is what a group of all automorphisms of a set of 4 letters, group of all permutations of 4 letters. So can it have exactly one silo 3 subgroup? That's very improbable, right? Because what is a silo 3 subgroup? A silo 3 subgroup of S4, as we can see here, is precisely a subgroup of order 3, right? That is, it is a cyclic subgroup, right, of order 3, which means that any silo 3 subgroup will consist of 2 elements of order 3 for sure, right? So if there is exactly one silo 3 subgroup of order 3, then S4 should have exactly 2 elements of order 3, right? No other element of order 3 can exist, because if we take any other element of order 3, that will generate a different silo 3 subgroup. But we have assumed that the number of silo 3 subgroups is 1, right? So if number of silo 3 subgroups is 1, then S4 has exactly 2 elements, right? 2 elements of order 3. But that is a clear contradiction, right? Because S4 has at least 3 elements of order 3 that we know. But these elements, so if you take, so hi Ravi, and okay, thank you for joining. Yeah. So, but if, yeah, what was I saying? So yeah, so but if S4, but we know that S4 has at least 3 elements of order 3, right? Namely, we can take 3 cycles, 1, 2, 3, this is an element of order 3, 1, 2, 4, this is an element of order 3, 1, 3, 4, this is an element of order 3, right? Are elements of order 3, right? So this is a contradiction. This is a contradiction. To what? To our assumption that the number of silo 3 subgroups of S4 is 1, right? Hence, we know that the number of silo 3 subgroups has to be 4. Hence, S4 has exactly 4 silo 3 subgroups. And it's as simple as that. So it's as simple as that. So we have found out that the number of silo 3 subgroups of S4 is precisely 4. There are exactly 4 silo 3 subgroups of the symmetric group on 4 letters. So for those who joined a bit late, let me just sort of go through the argument in a brief way again, that we first use the Silo's third theorem to conclude that the number of silo 3 subgroups can be either 1 or 4. Now since S4 has at least 3 elements of order 3, namely we can take 3 cycles, 1, 2, 3, 1, 2, 4, 1, 3, 4, they are inverses as well, so you get at least 6 elements and so on. So the point is the number of silo 3 subgroups cannot be 1, because observe that if you have exactly one silo 3 subgroup of exactly one silo 3 subgroup which is precisely a subgroup of order 3, then that means that S4 has exactly 2 elements of order 3, but we clearly stated at least 3 elements of order 3, namely these 3 cycles that we have mentioned here, right? So S4 cannot have one silo 3 subgroup of one silo 3 subgroup, it has exactly 4 silo 3 subgroup, right? Yeah, so it's simple. Okay, so let's come to the second problem. And by the way, I am still audible, right? Everyone can hear me? Just confirm in the chat.
Yes, sir.
Okay. So yeah, so this is a question that I had discussed previously in maybe week 2. I mean, not exactly the same question, but the trick involved was discussed there, but still we'll go through this once again. So let's read it out. So let G be a group of order p to the power k m, where p is a prime, p is not dividing m, and you are given that m and k are greater than 1. Okay, so we don't need k to be greater than 1. So k just can be greater than equal to 1. So let's just take m, so we need this assumption here, that m is strictly greater than 1 and k is greater than equal to 1, right? Yeah, so suppose G is a group of order p to the power k m, where p doesn't divide m and m is strictly greater than 1 while k is greater than equal to 1. So you are given this assumption that if cardinality of G is strictly greater than m factorial, then G cannot be simple. This is your statement, and you are asked to find out whether this statement is true or false, right? So first of all, let me ask you, what do you know what a simple group is? Maybe anyone can write down in the chat, or just unmute yourselves and let me know. Do you know what a simple group is? I think it was covered in the tutorial yesterday by Harish, right? You are solving problems on simple groups. So just maybe can, even if you don't know, just respond and let me know that you don't know. So do you know what a simple group is? Okay, so let me just, okay, so let me just state the definition once again. So a group is called a simple group. So just let's try to understand the point. So a group is called a simple group if it has no non-trivial normal subgroups other than the trivial subgroup and the improper subgroup. Okay. So what I mean by this is, you take any group G, you always know that the trivial subgroup of the group and the entire group both are normal subgroups of itself, right? So if the group doesn't have any other normal subgroup other than these two, that is the trivial one and the entire one, the improper one, then the group is called a simple group. Why am I calling it simple? Because you cannot take a non-trivial quotient of the group, right? So basically, if you take the group and if you quotient it by its trivial subgroup, you get the group, and if you quotient it by the entire group, then you get the trivial group, right? So the group cannot have any non-trivial subgroups, normal subgroups other than these two subgroups, right? That means you cannot obtain a non-trivial or a different quotient of the group. That is why we are calling it a simple group. Okay, so that's the definition. So the problem here is very simple. You are given a finite group of order p to the power k m, where p doesn't divide m and m is strictly greater than 1, k is greater than equal to 1. You are given that the cardinality of G is strictly greater than m factorial, then the group cannot be simple, which in other words, if this statement is true, you are required to find out whether this group contains a non-trivial normal subgroup, right, which is proper non-trivial normal subgroup, that is a normal subgroup of the group which is different from the trivial subgroup and the entire group, right? So as you know, so we claim that this statement is indeed a true statement. Okay, so we will indeed proceed to find out a normal subgroup of the group which is different from the trivial subgroup and the entire group. And the basic idea is that we know that normal subgroups have a have a characterization, right? We can characterize normal subgroups as precisely kernels of group homomorphisms, right? So precisely we'll try to find out a group homomorphism and we'll look at its kernel and we'll claim that this particular kernel will be your required normal subgroup. Okay. So the way to construct this is very simple. So this is your main hint that the cardinality of G is strictly greater than m factorial. Since m factorial has come into the picture, you understand that some sort of symmetry group comes into action, and hence what we mean is that there has to be some sort of action going on, group action. Okay. So first of all, can you tell me that the group, does the group G contain a subgroup whose index is m? Do you have this? The group has order p to the power k m, where p is a prime and p doesn't divide m. Does this group have a subgroup whose index is m? It's by side. Yes, 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 yes. Ravi, what were you saying? Okay, so basically by Silo's first theorem, let H be a subgroup, or more precisely, let H be a Silo P subgroup of G, right? So we know that G is to H, that is the index of H in G is precisely m, right? So now what we do is we do a trick here. So let omega be the collection of left cosets of H in G, and we consider an action, the usual action of G on this omega, so we consider this action which is given by sending, so yeah, so defined by, this action is defined by G dot AH is GAH for all G in G comma AH in omega. This is your action. As usual, you can check that this is a well defined action and all that. So the point is, once we have an action of the group on omega, right, we know that groups capture symmetries of objects, right? So the group acting on the set omega basically means that you have a homomorphism. Thus there exists a homomorphism, which is a permutation representation of the action, right? Homomorphism from G into S omega, which is a symmetric group on the set omega. No, keep in mind that the index of H in G is M, and omega is a collection of all left cosets of H in G. So omega has exactly M factorial elements, right? It's the symmetric group on M letters. So this is isomorphic to Sm, we can say that. So we get a homomorphism from G into S omega or into Sm, doesn't matter. The point is we get a homomorphism from G into S omega, right? Group homomorphism. Now let me ask you this question. Can this homomorphism be injective? Just look at your hypothesis. Whatever is given to you, just look at that. Can this homomorphism be injective? You want to try? Maybe you can write down in the chat. Can this homomorphism be injective? Nah, no, that's not the answer. P does not divide M doesn't imply that this homomorphism can be injective, right? It since the you what you are trying to say is that G is, if this homomorphism is a monomorphism or is an injective map, then G is isomorphic to a subgroup of S omega, and hence the order of G divides the order of S omega, which is M factorial. But that can't happen because P doesn't divide M. But you don't know, right? Because M might be very large, and M factorial might contain powers of P, no? M factorial might contain powers of P. So this homomorphism, so at the end of the day, cardinality of G might divide M factorial, right? I mean, it doesn't divide because of this assumption, but just by saying that P doesn't divide M won't work, right? You need this fact that cardinality of G is greater than M factorial. This is what is actually helping you here, not the fact that P doesn't divide M, right? So anyways, nice try. So the point is that this homomorphism, since cardinality of G is strictly greater than M factorial, so let's call this map sigma, let's say. Sigma is, this arrow sigma is not injective, right? And what do we know about homomorphisms which are not injective? We know that they have non-trivial kernels, right? So consider kernel of sigma which is certainly non-trivial, right? Because sigma is not injective. So we at least have found, we know that kernel of sigma is always a normal subgroup of G, and we at least have found out a subgroup, normal subgroup, which is different from the trivial group. But still there is no guarantee, right, that this subgroup might not be the entire group G, right? It still might be the entire group G, in which case it certainly is not proper, right? It can be improper, but it can't be improper. Why? So if kernel of sigma is equal to the entire group G, that is every element of the group is in the kernel, which means that every element of the group is getting mapped onto the identity permutation of S omega, right? Which means that every element of the group, whenever acts on any left coset that is an element of omega, it keeps that element fixed, right? In particular, what this means is that every element of the group fixes the left coset EH, right? That is the coset containing the identity, right? So if kernel of sigma is G, then for all G in G, we have G dot H is equal to H, right? And what does this mean? G dot H by definition of the action is just GH. So you get GH is equal to H, and you know that whenever GH is equal to H, if and only if G belongs to H, right? So we get that for all elements G in G belongs to H, which implies further that G is equal to H, right? But can this be true? Can the subgroup H, which is a Psylopy subgroup of G, can this be exactly equal to G? No, right? Because of this assumption that m is strictly greater than 1, right? Isn't it? Simply because of this assumption we are done, right? Since m is strictly greater than 1, we know that h has to be a proper subgroup of G, right? That is, the cardinality of h is strictly smaller than the cardinality of G, right? So this is again a contradiction. Since m is strictly greater than 1, right? Thus, kernel of sigma is a proper subgroup of G. And we have clearly found out that the kernel of sigma is different from identity, right? So we have found out a non-trivial normal subgroup of G which is proper, which is not the entire group. Hence, G is certainly not simple. And that's it. So the statement is indeed true. G cannot be simple. So this is something very important that you should keep in mind. At times you need to find out whether a group is simple or not, and this kind of criteria will actually help you do it very easily. Anyways, so let's come to the next problem. So this is something very nice. So you clearly know what Fp is, right? First of all, Fp is a finite field with p elements, right? That is Zp in other words, where p is a prime. So assume P is a prime, you are asked to find out the order of the Silo P subgroup of a, you are asked to find out the order of a Silo P subgroup of GLN FP, right? Where n is greater than equal to 1. So in other words, you just need to find out the order of GLN FP, or more precisely, you need to find out the you need to find out what is the largest power of P dividing the order of GLN FP. So you know GLN FP, right? It is precisely the set of all n cross n matrices, rather the group of all n cross n matrices with elements or entries from Fp, the finite field with p elements. So to solve this problem, we are going to use some amount of linear algebra, right? So first of all, just recall this, that GLN FP, which is precisely the set of all, the group of all n cross n matrices, invertible n cross n matrices with elements from Fp, this is, as a group, is isomorphic to the group of all linear isomorphisms, rather automorphisms, linear isomorphisms Fpn to Fpn, right? So you know vector spaces, I assume, and you know that every linear map from one finite dimensional vector space into another is nothing but a matrix, right? For a fixed pair of ordered bases of the domain and the codomain. And what are those kind of matrices? What are those kind of? I mean, what do those matrices correspond to? Which are actually invertible matrices? They precisely correspond to isomorphisms, right? So basically, multiplication of matrices is basically translates to composition of linear maps, right? So so GL and FP, the set of all, the group of all n cross n matrices, n cross n invertible matrices over Fp is precisely isomorphic to the group of all linear isomorphisms from Fpn to Fpn. In other words, the group of all automorphisms of Fpn, vector space automorphisms of Fpn, right? And you know that what is an isomorphism essentially determined by, right? You know that an isomorphism sends a basis onto a basis, and any map which sends a basis onto a basis extends uniquely to a linear isomorphism from the domain to the codomain, right? So precisely what we are asked to find out here is, so consider the standard basis, standard ordered basis, let's say E1. We are taking an ordered set here, E1 up to En of Fpn. So you understand, right, what I mean by E1. E1 is precisely that vector, which column vector, which contains 1 at the first coordinate and all the coordinates below are 0. E2 contains 1 in the second one and all the rest of the coordinates are 0, and so on up to En. So this is a standard ordered basis of Fpn, right, that we know. And what does a linear isomorphism do? It takes this ordered basis onto some ordered basis of FPN, and conversely, if you take any set map that takes this ordered basis onto some ordered basis of FPN, then this set map gives you a unique linear isomorphism from FPN onto FPN, right? So in other words, the number of linear isomorphisms, or rather maybe let me just shorten it out, linear automorphisms. Automorphisms are just isomorphisms of some object onto itself. So linear automorphisms of FPN is equal to the number of ordered bases, right? And I precisely gave you a recipe for cooking up this correspondence, right? Basically what you do is you take an isomorphism, you map it onto what, onto which ordered basis, just take the images of E1 E2 up to En under this isomorphism, you get an ordered basis there. And conversely, if you are given an ordered basis, what you do is you take a set map that maps E1 onto V1, E2 up onto V2, and up to En onto Vn, and you extend this to a unique linear isomorphism from FPN to FPN. So this is what it is, and hence we can say that the number of linear automorphisms of FPN is equal to the number of ordered bases of FPN. So it all boils down to finding the total number of ordered bases that FPN has as a vector space over FP, right? So and the trick is very simple, right? So just keep in mind, what is an ordered basis? It is an ordered collection of vectors, right? FPN has dimension n over FP, so you are required to find out the number of ordered bases of FPN, and you know that any ordered basis has n elements, so you just need to pick an ordered collection of n linearly independent vectors, right? And you need to find out in how many ways you can do this. The answer is very easy. So what you do is, so you let me just maybe draw a rough diagram to explain. So you take, let's say you first pick a non-zero vector, right? Since it has to be, this vector has to be in the basis, you can't take zero vector, right? Zero vector is always linearly dependent with anything. So you take a non-zero vector. So take a non-zero vector, or maybe let's just write this, number of ways of choosing a non-zero vector is, so you have total p to the power n elements, and you have exactly one non-zero vector, one zero vector, right? So the number of non-zero vectors is p to the power n minus 1, and hence you can choose a non-zero vector in p to the power n minus 1 ways, right? Now observe, what you need to do next is you need to pick a second element of your ordered basis, right? I mean second vector which is linearly independent with this particular chosen vector, right? So let's call this chosen vector to be V1, right? And by this shading I mean the span of V1, right? So if V2 has to be linearly independent from V1, V2 has to be chosen outside the span of V1, right? So basically what this means is you take V1 and you find out the number of elements in the span of V1. Since the underlying field is FP, the finite field with P elements, so the number of elements in the span of V1 is precisely P, right? So you need to choose V2 outside this, so you have precisely P to the power n minus P choices for V, right? So number of ways of choosing second non-zero vector, and keep in mind this has to be linearly independent from V1, right? Second non-zero vector is p to the power n minus p, right? So you have this, so this is V1, so let's say you have chosen something V2 outside V1, right? And you just go on continuing this. Again you find out the span of V1 and V2, I mean the number of elements in the span of V1 and V2. Precisely since Fp has P elements, and any vector in the span of V1 and V2 can be uniquely written as lambda 1 V1 plus lambda 2 V2, This is all vector space knowledge, right? Since this is true because v1 and v2 are linearly independent, any vector in the span of v1 and v2 can be written like this. So you have p choices for this one and you have p choices for this one. So basically you have p square choices, right? So basically there are p square many elements in the span of v1 and v2, right? So you have to choose v3 outside this span. So the number of ways of choosing I should write linearly independent here. Independent vector. Third linearly independent vector. P to the power n minus p square, right? So you get v3 here and you just continue this procedure. You again find out the span of v1, v2 and v3. You choose something outside this and you stop when you arrive at vn, right? So the point is, thus the number of ordered bases of fpn is, let me just write down a symbol for ordered basis so that it helps you understand better. Thus the number of ordered bases v1, v2 up to vn of fpn is precisely p to the power n minus 1 times p to the power n minus 2, minus p square. So let me write this below. P to the power n minus 1 times p to the power n minus p square times p to the power n minus p cube dot p to the power n minus p to the power n minus 1, right? This is your total number of ordered bases of fpn, and hence you know that the number of linear automorphisms of fpn, or in other words the number of elements of gl and fp, is precisely this number, right? Hence cardinality of gl n fp, we have found out this finally. This is precisely p to the power n minus 1 times p to the power n minus p square times p to the power n minus p cube and dot so on, p to the power n minus p to the power n minus 1, right? So now from this it's very easy to find out the largest power of p dividing largest power of p dividing your dividing the order of gl and fp. So what you do is you just factorize this. You just find out the largest power of p in this number, right? So from the second coordinate you get p square, from third you get p cube, and from the last you get p to the power n minus 1, right? Okay, I missed out a p here. Yeah, so you have p here and you have p to the power n minus 1 here, right? So this is p square, and it goes on, right? So from the first one you take out p, from the second one you take p square, and so on, right? Hence p to the power n minus 1. So so basically you get this, that the cardinality of gl and fp is equal to p. You get p from the first one, you get p square from the second one. I mean from this one you get p, from this one you get p square, from this one you get p to the power n minus 1. So p to the power 1 plus up to n minus 1 times p to the power n minus 1 times p to the power n minus 1 minus 1 times p to the power n minus 2 minus 1, and it continue this, you get p minus 1 ultimately. So this is just p to the power n minus 1 into n by 2 times this thing, right? So let me write it in shorthand notation. P to the power I minus 1, where I goes from 1 to n, right? So this is your factorization in terms of prime p, right? So, and clearly p, also observe that p doesn't divide this second factor, right? And that's very obvious, right? Because P is a prime, and if P divides this particular product, then P must divide at least one of the elements in this product, right? So that means if P divides anything, if P divides this product, then P must divide some P to the power I minus 1, but that is a clear contradiction, right? I runs from 1 to n, so P to the power I is at least P, right? So P certainly divides P to the power I, from which you get P divides 1, right? And that's an obvious, that's an impossibility. A prime cannot divide 1, right? So in other words, what you can say is, since P doesn't divide this product, hence the order of a silo P subgroup of GL and FP is P to the power n minus 1 times n by 2. Right? So this is your order. Any silo P subgroup of GL and FP is P to the power n minus 1 times n over 2. Right? So yeah, maybe let me write it more clearly, otherwise. So is P to the power n times n minus 1 by 2. This is what it is. Not only so, you can in fact find out the number of silo P subgroups of GL and FP, which is one other question that I have given here. But since we don't have much time, I'll rather solve this here and let you know. But yeah, this is not difficult again. The basic idea is you know that the number of silo P subgroups of a group is equal to the order of G over the order of the normalizer of any particular silo P subgroup, right? So the trick is to find out one silo P subgroup of GL and FP, and that is precisely given by the upper triangular matrices with 1 in the leading diagonal, right? That gives you a silo P subgroup. It's very easy to check. And the next what you do is you try to find out the normalizer of that silo P subgroup, and once you find out the normalizer, you just divide the order of G by the order of the normalizer to get the number of silo P subgroups. So that is a brief description of the way we can find out the number of silo P subgroups of GL and FP. I'll write it down, and when I share you can see. So let's go to the next question. Okay, so this week you were introduced to free groups, right? Can someone confirm? Were you introduced to free groups this week? Ravi? Yeah, Shalini, yeah.
Yes, sir.
Okay.
This week we have learned about free groups.
Okay, cool. So you understand what a free group is, right? Precisely, it is a group that has some set of generators which is free of any non-trivial relations. That is, yes, that is what a free group is. But those kind of definitions are actually very boring in mathematics. The main things that are important is how one object is sort of related to another object. You are interested more in the connections between objects rather than how the objects actually look internally, right? So what I mean is, free groups come with a very nice characterizing property which is entirely given in terms of maps. You are not interested in how the free group looks internally, right? You are only interested in what are the maps coming out of the free group. So this is the so-called universal property of free groups that characterizes free groups. So let me write down, and this is very important because once any group satisfies this property, it becomes a free group. You don't need to look internally or try to find out some free set of generators and all that. You don't need to do all that. So objects, this is one of the themes of math, right? That an object, any kind of object, group, field, ring, vector space, even a set, anything, any object is fully determined by the maps going into it or the maps coming out of it. This is a very deep principle in mathematics, in category theory. So let's not digress so much. Let me just write down the universal property of the free group. So what can I say? So let S be a set let Fs be the free group. On S. You know what this is. You have constructed it internally, so you understand what Fs is. So the universal property is this, that so you also have a map, right? So you have a map S into Fs, the inclusion map, right? So the universal property is this. So this has the following universal property. So given any group G and any set map, let's call it F from S to G, which maps S into G, there exists a unique group map, that is a group homomorphism, f of S, I mean from f of S to G, let's call it phi, such that a particular diagram, a particular triangle commutes. In other words, such that you have this equality of composition, that so you have Fs going and S coming into Fs. Yeah, so phi composed F is equal to, sorry, let me call this I. Okay, so phi composed with I, yeah, is equal to F. So this is what your universal property of the free group is, right? And once you know that if you are given a group F and a set S and you have a map S into F such that it satisfies this universal property, that given any group G and any set map from S to G, you get a group homomorphism of F into G such that this composition holds, this equality holds, then you can fully be sure that the group F that we are talking about is a free group and it is generated by the map S into Fs. I mean it is generated by the image of the map from S into Fs, right? So this is a universal property of the, this is the universal property of the free group and very important. So you better sort of understand what is going on. Precisely what this says is that any set map from S into any group can be uniquely extended to a map on the entire free group. That is, you get a unique homomorphism from Fs into G. See, what is the problem with defining homomorphisms from one group into another? Homomorphisms must satisfy the fact that they should preserve the composition, that is, they should preserve the structure in the group, right? The operation of the group, right? So it's not that you take any subset of a group and you can map it freely to any other group and that map extends to a homomorphism from the domain into the codomain, right? It's the a number of I mean, it's absurd to even assume that. But this kind of abstraction is not present for free groups, right? Why? Precisely because the set S, which is a part of the free group, is actually free of any non-trivial relations. S doesn't satisfy any kind of non-trivial relations, right? So what this property says is that you can map S freely into the group G, right? You can map S freely into the group G, and regardless of whatever mapping of S into G you are taking, you can always get a unique group homomorphism from the free group into G, which sort of extends this particular map from S to G. That is what the universal property is all about. So let's just focus on the question right now. So it says that a group which is generated by two elements is a quotient of the free group on two symbols. You know what the free group on two letters is, right? You have studied free groups this week. So what this question is asking you to find out is, you are taking a group with exactly taking a group which is generated by a set of two elements. You need to find out whether this is a quotient of F2, the free group on two letters. What is the difference between F2 and this group? F2 is generated by a set of two elements, just the fact that there are no non-trivial relations between these two elements, right? While this group which is generated by two elements can satisfy, I mean the two elements, two generating elements can satisfy non-trivial relations between them, right? That's the only difference. And how this one is again true. And how do you get this? The basic idea is just to use the universal property of the free group, right? So coming to the question, So consider, or maybe let's suppose let G be a group generated by, let's say, x comma y. That is, x comma y is a subset of G which generates G. There are relations. I mean, G is a given group. You take a generating set x comma y which generates G, and there might be relations, right? So what you do is consider the set map from a set AB into G, which sends, what does this map do? It maps A onto X and B onto Y, right? So now, by the universal property of this, of the free group generated by AB, you know that there exists a unique group map or a group homomorphism from the free group F2 into G, right? That extends the original map from AB into G. That is, that maps A onto X, B onto Y, right? And finally, you can check that this map that you have taken from F2 into G is actually an epimorphism, right? That is, it's a surjective map. Surjection, right? That is, it's like this, right? Yeah. This is the usual notation for surjections, right? You have the original arrow and you add this head here, one more arrow here. I mean, one more head or whatever it is. This is the notation for a surjection. Anyways, so once you have a surjective homomorphism from F into G, you know that hence G is isomorphic to F2 mod kernel, right? That is, G is a quotient of F2. By the way, why will this map be surjective? Precisely because it maps generators onto generators. A is mapped onto the generator X of G, B is mapped onto the generator Y of G, right? So once you have a mapping of generators onto generators, the extended homomorphism will obviously be surjective. There's no doubt about that, because every element of G can be written as a product of X and Y, since X and Y are generators here. Some product of powers of X and Y, negative, positive, etc. So you have this. So any group which has a generating set of 2 elements is a quotient of F2. Any group which has a generating set of n elements is a quotient of Fn, free group on n letters. In fact, any group which has a generating set, let's say, how should I say this, which has a generating set with alpha elements, where alpha is some cardinal number. It might be finite, it might be infinite, doesn't matter. Then that is a quotient of the free group generated on those number of elements. Okay. So anyways, this is something that I wanted to say, because since you have started learning free groups, this is a very important thing that you must notice. Universal property which characterizes the free group object as an object in its own right. You don't worry about how it looks internally. You are only concerned about what are the maps going out of this, and that is enough to understand the free group. Okay. So let's come back to Seiler's theorem once again. So again, the material will be a bit lighter from now on. So a very simple problem here. So you are asked to find out the number of Silo 3 subgroups in a non-cyclic group of order 21. So you take a non-cyclic group of order 21 and you are required to find out the number of Silo 3 subgroups that this has. So first of all, you clearly know that 21 is 3 times 7. Yeah. So by Seiler's third theorem, the number of Silo 7 subgroups, which you know is of the form, so n7 equal to 1 plus 7k, must divide 21, which implies 1 plus 7k must divide 3, since 1 plus 7k is relatively prime to 7, right? So So this implies that N7 is equal to 1. So the number of silo 7 subgroups is precisely 1. So let's try to talk about the number of silo 3 subgroups. So N3, which is the number of silo 3 subgroups, is of the form 1 plus 3k, which again divides 21, which implies 1 plus 3k divides 7, since 1 plus 3k is relatively prime to 3, right? We are only using Silo's third theorem here, and the fact that the number of silo p subgroups must divide the order of the group. That's it. So from this you get that N3 is 1 or 7, right?
7.
Yes. Yes. You're saying something?
No, sir. No. I said 7.
Yeah, okay. 1 or 7, right? Yeah. So, yeah. So if N3 is equal to 1, that is the number of silo 3 subgroups is equal to 1, what happens? Okay, let's see. So there is a unique silo 3 subgroup which has to be normal therefore, right? So let H be the unique silo 3 subgroup, and we have already found out that the number of silo 7 subgroups is 1. So there is exactly one silo 7 subgroup, and K be the unique silo 7 subgroup. So what does that mean? So you have H, the unique silo 3 subgroup of G, K the unique silo 7 subgroup of G, and both are clearly normal in the group, right? Because since there is exactly one silo 7 subgroup, so any GK G inverse which will have the same order as K must also be a silo 7 subgroup, and since there is exactly one silo 7 subgroup, K has to be its own conjugate, right, for every G. Similarly, H has to be its own conjugate for every G, from which we get that both H and K are normal in G. So now HK is equal to KH, that we know because H is normal or K is normal, therefore HK has to be equal to KH, and order of HK. So what this precisely implies is that HK is a subgroup of G. You know, right, that if you are given subgroups H and K, HK is a subgroup if and only if HK is equal to KH. And what is the order of HK? This is order of H times order of K over order of H intersection K. Now order of H is 3, order of K is 7, and what is the order of H intersection K? Just keep this in mind that H intersection K is a subgroup of both H and K, right? Therefore order of H intersection K divides the order of H and it divides the order of K, right? Yeah, I understand what you are saying. So it has to be 1, right? Since 3 and 7, so order of H intersection K is a common divisor of 3 and 7, and since 3 and 7 are relatively prime, so this means that this is 1. So order of HK is 21, which implies that HK is precisely the entire group G, right? Okay, so G can be written as HK. H intersection K is trivial. H and K are normal in G, which means that G is an internal direct product of H and K, right? That's it. So G is an internal direct product of H and K, and from this we can conclude that the group G that we are talking about is actually cyclic. Why? Because yeah, the best way to understand this is, then how should I say this? G is isomorphic to H cross K, right? G is isomorphic to H cross K. What is H? H has precisely 3 elements, right? So this is just Z3. There is one group of order 3, Z3, and there is exactly one group of order 7, right? Because 3 and 7 are primes, right? They are the cyclic groups. So G is isomorphic to Z3 cross Z7, which is therefore isomorphic to Z21. You know this, right? That Zm and Zn are if Mn, I mean Zm cross Zn is isomorphic to Zmn if and only if M and N are relatively prime, right? Yeah. So G becomes isomorphic to Z21, which is a contradiction, as G is non-cyclic. I mean, we could do this without using these isomorphisms and all that. We could do everything internally, right? That we could just take, since H is abelian and K is abelian, we could show that HK is abelian precisely because what you do is you take any element A in H and any element B in K, you consider this product A, B, A inverse, B inverse. So A, B, A inverse, B inverse. A is in H, B is in K. Now just keep in mind that since H is normal, so this is an element in H, this is an element also in H. So this product belongs to H, and at the same time, since K is normal, this conjugate of the element B in K by an element A is in K, and this is in K. So this is also in K. So this element A, B, A inverse, B inverse is both in H as well as in K, right? So it's in their intersection, but the intersection has been shown to be trivial, right? Which means that A, B, A inverse, B inverse has to be identity, which means that AB has to be BA. So the group is abelian, and once you know that the group is abelian, what you do is you take an element of order 3 and you take an element of order 7, you take their product, that will be an element of order 21. In other words, the group will be cyclic. As simple as that. So we could either go externally by using all these isomorphisms, or we could just work internally. Everything suffices, everything works. So the point is that we get a contradiction at the end that the group is cyclic. But the group was assumed to be non-cyclic group of order 21, right? And this contradiction arises because we have assumed that n3 is 1, right? So n3 cannot be 1. Hence, the number of Silo3 subgroups is n3 equal to 7. So it has exactly 7 Silo3 subgroups, and simple as that. So moving on to the next problem. So you are asked to find out the number of Silo3 subgroups of S5. So let me just quickly go through the argument. So just recall that S5 has 120 elements, right? So cardinality of S5 is 120, and this is help me check if I'm correct. So 2 cube into 3 into 5, right? Because yeah, so 2 cube into 3 into 5, and hence the order of any Silo3 subgroup of S5 has to be 3, right? So you are asked to find out the number of Silo3 subgroups of S5. So the number of Silo3 subgroups of S5, just a moment. Yeah, it's of S5 is in 3 equal to 1 plus 3k by Silo's third theorem, and we know that 1 plus 3k divides, this number should divide 120, right? Which implies 1 plus 3k should divide 40, right? And what are your possibilities from this? So the only possibilities are thus n3 is equal to 1, or it has to be 4, or it has to be 10, or it has to be 40. These are the only possibilities that you have here. Right? Now we claim that n3 has to be, cannot be 1 or 4, right? Why? Because just observe that S5 has at least 5 choose 2, which is 10 elements of order 3, right? Namely, which are those elements? Those are the 3 cycles, right? So you have 5 symbols. You just want to find out the number of 3 cycles, or rather you want to find out some 3 cycles, right? So any 3 cycle is given by 3 elements. Just for the time being, forget the ordering of the elements. So this is 1 3 cycle, this is also 1 3 cycle, right? So we'll just forget the ordering. The number of selections of 3 elements has to be 5C3, that is 5C2, right? Which is 10, right? So basically what I'm saying is there are at least 10 different 3 cycles, right, of S5. Hence the number of Silo3 subgroups cannot be 1 or 4, right? Because the number of Silo3 subgroups, any Silo3 subgroup contains 2 elements of order 3, right? And any 2 distinct Silo3 subgroups have to be, they have to intersect trivially, right? Very simple to understand, right? So in other words, if there are 4 Silo3 subgroups of S3, then the number of elements of order 3 is precisely 8, right? You have 2 in the first one, you have 2 in the second one, 2 in the third one, and 2 in the fourth one. but you have clearly found out at least 10 elements of order 3, right? So hence n3 is equal to 10 or n3 is equal to 40. That is, the number of silo 3 subgroups is either 10 or it is 40, right? Now let's try to understand something. Let us simply try to find out what are those elements in S5 which have order exactly 3. You know, first of all, that 3 cycles of order 3, right? But it can be possible that some other kind of element has order 3, which is maybe a product of 2 cycles and all that, right? So just recall that recall that every element in S5 has ordered exactly, yeah, so what I was saying is, what was I saying? Yeah, you know that every permutation can be written as a product of disjoint cycles, right? So let's try to find out the number of ways you can write number of ways or number of possibilities that you have here, right? So that is precisely, a permutation can be of this form, right? That is, it is a 5 cycle. So let's just, okay, so let me write it clearly. So any permutation of S5 can be of the following forms, rather one of the following forms, exactly one of the following forms. So you have either a 5 cycle A1, A2, A3, A4, A5, or you have a 4 cycle A1, A2, A3, A4, A5, or together with a 1 cycle, and all these are disjoint, right? You can write any permutation as a product of disjoint cycles. So or it can be A1, A2, A3, a 3 cycle together with a 2 cycle A4, A5, or it can have the form A1, A2, A3 together with 1 cycles A4, A5, or it can be of the form, let's say, A1, A2, a 2 cycle together with a 2 cycle A3, A4 together with a 1 cycle, or it can be of the form, let me write it here, or it can be of this form that it's the identity permutation A1, A2, A3, A4, A5, right? Or it can be of the form that it's a 2 cycle A1, A2, and then you have 1 cycles A3, A4, A5, and finally what it can be is it can be a 3 cycle, right? Oh, we have written that 3 cycle together with 1 cycle. So these are the only possibilities that an element of S5 and any element of S5 belongs to one of these classes, right? Either it is of the first form or it is of the second form or third, fourth, fifth, sixth, seventh. That is, you are just finding the number of partitions of the integer 5. That is what you are doing, right? So let's try to understand which of these kind of elements can have order 3, right? So clearly a 5 cycle can't have order 3. The second one, so this doesn't have order 3. So let me use a different color. So this doesn't have order 3, right? This doesn't have order 3. This also doesn't have order 3, right? Why? Because you know that the order of a product of disjoint cycles is the LCM of the orders of the cycles, right? So this third one has order 6. It cannot have order 3. The fourth one has order 3. It's precisely a 3 cycle. It has order 3. The fifth one cannot have order 3. It has order 2. The first one, this on the right, the first one cannot have order 3. It has order 1. It is identity. And the second one on the right also has order 2. So it doesn't have order 3. So precisely what we are trying to say is that an element in S5 has order 3 if and only if it is a 3 cycle, right? So we can say that thus an element of S5 has order 3 if and only if it is a 3 cycle. right? That is what we have said. And what is the total number of 3 cycles? You know that if you take, so precisely what are the number of ways you can pick out 3 cycles, right? From a, uh, I mean, I mean, so what I'm trying to say is the total number of 3 cycles has to be, we have found out at least, I mean, yeah, let me just say it precisely. So the number of 3 cycles of S5 is, so A1, A2, A3, right? You just need to select 3 symbols, and you need to keep in mind, or keep in mind the ordering also, right? So the number of selections of 3 symbols from 5 symbols, we have clearly found that is 5 choose 3, right? And what is the number of ways of arranging A1, A2, A3 in a cycle? That is precisely 2 factorial, right? You know that the number of arrangements of n objects in a circle is n minus 1 factorial. So the total number of 3 cycles is just 5c3 into 2. So it's 5c3 into 2 equal to 20. Not more than that, right? And hence, so what were the cases that we are left with? So N3 is 10 or 40, right? The number of silo 3 subgroups has to be 10 or 40. Clearly it can't be 40, right? We know that any silo 3 subgroup only consists of 3 cycles, that is 2 3 cycles and 1 identity element. And any 2 silo 3 subgroups are clearly intersecting trivially, right? Any 2 subgroups of order 3 will intersect trivially. Into distinct subgroups will intersect trivially, right? So what that means is it cannot be 40, right? Because if the number of silo 3 subgroups is 40, then the total number of elements of order 3 is 40 times 2, which is 80. But we have found out that the number of elements of order 3, that is the number of 3 cycles of S5, is 20. Hence, the number of silo 3 subgroups has to be 10. So this is the correct answer. Okay. So the number of silo 3 subgroups of S5 is precisely 10. So we have time for one more problem. So we'll solve this one and we'll end the session today. So very simple problem. You are asked to find out which of the following statements are correct. So the first statement is saying that there exists a group of order 375 with no subgroup of order 15. So just write 375 as, can someone factorize this for me? Maybe 5 7s are 35, 75, 3 into 5 cube, right? If I am not very wrong. This is 3.
Yes, sir. Correct, sir.
Yeah, this
Correct.
is 3 into 5 cube. Thanks, Ravi. So the point is, yeah, so so in 5, the number of silo 5 subgroups, that is the number of subgroups of order 5 cube, is 1 plus 5k, and it divides 375, that is 1 plus 5k divides 3, right? From which you get that n5, which is 1 plus 5k is 1. So there is exactly one subgroup of order 5 cube, and which therefore has to be normal. So let k be the unique normal subgroup of order 5 cube, right? And yeah, so again n3, which is of the form 1 plus 3k, must divide 125, right? That is 5 cube, from which we get that 7, yeah, so it has to be either 5, which can't be possible, so it has to be, so n3 is 1, or n3 is equal to yeah, it's 25, right? Yeah, so 1 plus 3k is 25, that can happen. So what happens if n3 is equal to 1? So if, so we consider two different cases, right? So case 1, n3 equal to 1, let H be the unique silo 3 subgroup, which therefore has order 3, right? So in that case, you can find, you can show that, so what you do is, I want to find a subgroup of order 15, right? So I have a group of order 3 and both are normal, right? So then, as was the argument previously done, so then the group is isomorphic to H cross K, as we had done previously, and and how should I say this? So H cross K is a group of order 375. H has order 3, K has order 125. Okay, so let A be an element of, okay, we can do one thing, right? We don't need all these things here. So what we can do here is let H be the unique silo 3 subgroup. Yeah, we can do work internally only. So let A be an element of order 5 in K, right? K has order 125 by Cauchy's theorem or Seiler's first theorem. K clearly has an order element of order 5, right? So let K prime be a subgroup of K generated by A, be the subgroup of K generated by A. It's a cyclic group, A, right? Then HK is equal to K prime H, right? Yeah, we could just say that K, let K prime be a subgroup of K of order 5. So HK is equal to K prime simply because K is a normal subgroup, right? Or rather, I mean, sorry, HK prime is K prime H, since H is a normal subgroup. H is the unique silo 3 subgroup of the group. So it's clearly a normal subgroup, right? So HK is equal to is HK prime is K prime H, which implies that HK prime is a subgroup of G. And what is the order of this subgroup? Order of HK prime is equal to order of H times order of K prime divided by order of H intersection K prime. Again the same thing happens. H has order 3, K prime has order 5, and hence their intersection has order 1. So this has to be equal to 3 into 5 over 1, which is 15, right? Thus we have found out a subgroup, right? Namely HK prime of G, which has order 15 for the first case. Hence there exists a subgroup of order 15, right? So case 1 we have shown that if the number of silo 3 subgroups is 1, then there is a subgroup of order 15. Now let's look at case 2. So N3 is equal to 25. What if there are exactly 25 silo 3 subgroups? But this is even easier, right? Because you know that N3, you know this, that if if P is any silo 3 subgroup, then the number of silo 3 subgroups, that is N3, is equal to order of G over order of NP, the normalizer of P, right? This you know. And since N3 is 25, hence order of N of P has to be equal to 15, right? Precisely. But you know that NP is a subgroup of G, right? Since NP is a subgroup of G, hence again in case 2 there exists a subgroup of order 15, and you are done. So the point is that statement A, that there exists a group of order 375 with no subgroup of order 15, is clearly incorrect, right? Every group of order 375 must have a subgroup of order 15. We have done this in cases. Firstly, we have assumed that the number of silo 3 subgroups is 1. Then we show that there is a subgroup of order 15. Then we assume that the number of silo 3 subgroups is 25. Again, we show that there is a subgroup of order 15. And we are done, right? So maybe we can end the discussion here today. I'll just write down the second problem and the 8th one, and then share it so that you can see all this. And yeah, that's it from my side. So if you have any questions, you can ask me. So Ravi or Shalini, you have any questions so far? Otherwise we can end.
No, sir. Thank you so much.
Yeah, okay. And Ravi? Is it okay? Okay, so I hope you don't have any questions, and thank you for joining once again. And do attend Harish's session next week Friday. So he will again be solving some problems. So yeah, and thanks for joining. See you next week. Okay, so let me stop the recording.